The next example, example 2 in the chapter, deals with springs and Hooke's law. This is something also you wind up taking in high school physics. Let's imagine a spring sitting on the ground, and we know from experience that if you drop a weight on this thing, the spring compresses. However, if the weight's not too heavy, it kind of compresses down to some point and stops and reaches a new equilibrium. And then if we want to compress it more, we have to add another weight on top, and then that forces the spring down even further. So what this tells us is that there's not just a constant force that would compress this all the way. If we apply a force, it'll compress the spring part way, but then the spring starts pushing back harder and harder. In other words, the further you compress or stretch a spring, the harder it gets to compress or stretch it further. That's expressed in Hooke's law, which says the force needed to compress or extend a spring is equal to K times X. Now when we add this X term in there, that means that as you stretch it further and further, this is a constant times the distance stretched or compressed, the force gets greater. So a way to think about this graphically is we have a situation where this is the amount compressed, and this is the force. Since this is a constant, and this would be just the slope of a line, we get something that looks like that, where the force is equal to Kx. Therefore, if we apply a compressive force on a spring between 0 and 2, whatever we want to look at, then the area under this curve is going to be the amount of work done. Now in a way, of course, since that's a triangle, we could use a alternate geometric way of solving this problem. But let's see how we would do it in physics. Let's set it up in physics. And let's use the numbers that are in example 2. Basically, K is given to us as equal to 16, and we're going to compress the spring between 0 and 0.25. So we set up our equation, and work is equal to the integral from 0 to 0.25 of Kx, but K is 16, x dx, like that. We integrate this and we get 16x squared divided by 2, evaluate it from 0 to 0.25, but that's going to be, now this cancels here, this turns into 8, so we've got that, and then this, when evaluated between 0 and 0.25, equals 0.5. And then we'd supply the units, whatever, either Newton and meters, which would give us joules, or perhaps foot-pounds. And in the book, it's foot-pounds. But that's how it's done.